Okay, in this third tutorial video, I'd like to go over the stocks and flows modeling example script, which also is an opportunity to show how to use the mech447 package within a Jupyter notebook. But to start, I'll use the just Notepad++ and command prompt setup that I showed you in video 1. So if we go to our mech447 folder, there's this examples folder which is provided with the install, and there's a number of examples here for each of the modules. So we're going to start with stocks and flows example. So if I open that in Notepad++, just edit it. This is showing how to use the mech447 package to solve question 3 of assignment 1, for example. Well, the assignment that was part of when I took this course. So you'll notice that here, this part here is important. This is, we are appending to the Python path, and this just means we're appending the parent folder of where the examples live. So if I go up one, this is the parent folder, here's our mech447. So wherever you have this mech447 folder, you need to have it included on the path here. Here I'm just using relative path, but you could just as well use absolute path. So if I want to use the absolute path instead, what you can do is this folder that's containing mech447, if I click here in my file explorer, it'll show me the absolute path. So if I just copy paste this into here, that will also work. That will also work. Just need to change these path separators to forward slashes, because backslashes in strings are the escape character. So just change them to forward slashes, and then this should work. So you can either use relative path. So this would be relative to the folder containing the example. Right, so relative to this folder, we want to go up one. That's what the 2 dots means, and that brings us to where our mech447 folder is. Or if you'd rather just use absolute path, just go to where your mech447 folder is, click in the address bar, and you'll see the absolute path there. You can just copy paste that in. So that allows you to put this 447 folder anywhere you want on your system, and then keep your scripts in some other place if it makes more sense to do that. But we're just going to go with as provided, because I know everything's set up and it works. So here's our examples here. We need to have a command prompt running from this examples folder. So I open one up in the usual way. So just click here, type CMD, hit enter, and now we're running from our examples folder. So we're importing our stock flow module of mech447, and we're just aliasing it as SF. So this is how you import parts of the mech447 package. So for example, we are importing this module specifically. You could just as well import any of these other modules, and you'll see that in the other examples. But for now, we're just looking at stocks and flows. So stocks and flows. So what are we trying to actually do with this example? Well, we're modeling stock and flow dynamics. In this case, we're doing a 100-year modeling horizon, and we're doing steps of 1/1000th of a year. So however many hours that is. We're going to build up a time array. So here I'm just using NumPy linspace. So we're going from 0 to number of years in the number of steps. So we're doing 100 years, and then we're doing 1,000 steps per year. So that's our density times number of years. So this is just a uniform time series that spans that modeling horizon. And then we can define some of the constants. So we've got alpha and mu. Can't remember what those are for exactly. I think those are for the production and the resource addition to the reserve. I'd have to look back at the documentation. But anyways, this is where you set up the constants for your problem case. And then here we're going to set up, run, and plot the results for our stock and flow modeling case. So we have a few more inputs. We have the initial, I think that's addition rate is F. Yeah, so unconstrained addition. So this is how much could be added to the reserve if it was an unlimited reserve. So here we're just saying it's the initial megatons per year times this exponential. So we have mu per year, so that's the growth or decay rate in the addition. In this case, it's a decay rate because it's negative, and then multiplying into our time array years. So essentially, this is f naught times e to the mu t is what this array gives us. So this gives us our time series of addition rates in megatons per year. And then we have a source term. In this case, it's just zeros. So that means there is no source. So it's just a time series of zeros. And then we have our production in megatons per year. And again, it's just a simple exponential model. So P naught, that's our initial production in megatons per year. And then exponential of alpha per year. So that's our production rate. That's our alpha per year production rate. So it's exponential growth in this case because it's positive into the time array. So this is just P naught times e to the t. E to the alpha t, I should say. Our initial reserve state in this case is 0 megatons, and our maximum reserve megatons is numpy.infinity. So we're saying that our reserve is unbounded. We can put as much stuff in there as we want. Then we're going to create a stocks and flows instance. So the calling sequence is like this: pass in your time array, pass in your unconstrained addition, your source, and your production. And then you have the total resource. This is the total amount of resource that's available to be added to the reserve, and that's defined up here. So 1,000 megatons is all that's available in this case. The initial state of the reserve is 0. I'm just double clicking to highlight these things. And then the maximum reserve is unbounded, so we can put as much in the reserve as we want. And in this case, the unit string is megatons. So our measure of amount of stuff in this case is megatons. Then we run our stocks and flow class instance, and then we're going to plot some results. Right, and I'm going to put a breakpoint in there. Actually, we'll just look at this first part. So I'm just going to put in a breakpoint there, so it'll stop. Now, if I come over here and I invoke the Python interpreter and I run our example, stocks and flows example.py. If I just run it, we'll get a bunch of plots. There we go. All right, awesome. So what's the first figure? Aha, so here's the first figure. So the first figure is flows, so megatons per year versus time in years. And you can see everything labeled here. So we have our unconstrained addition, so that's the dashed line. And then the solid line is our constrained addition. Okay, and then again we have unconstrained and constrained source. It's just flat because there's nothing going on there. And then we have our unconstrained and our constrained production. So if the production was unconstrained, it would continue like this, but eventually it hits a constraint and it drops off. So the only constraint in play here is the amount of resource that's available. It's the amount of resource available. So we only have 1,000 megatons of resource available. So our unconstrained addition would be to follow this profile, but we're going along and it looks like at about, I'm using my mouse here, and if I read off the bottom right of this plot, it looks like about, I don't know, 10, 11 years. After about 11 years, we've added everything we can add. The total resource is depleted, so then it drops to 0 and it stays at 0 for the rest of the modeling horizon. And then our constrained production is following this exponential growth up until about, where are we, 65 years-ish? And then it drops to 0, because again, we've produced everything that's available. So this is a time series of rates. This is a time series of stocks, right? So these are our flows, these are our stocks. So we have the total available resource is the dashed line. So we see 1,000 megatons, that's our total available. The cumulative addition, so how much resource has been added at every point in time. So we see this growing up until 1,000, and then it just flatlines because that's everything that's available. In our reserve, we see that if I put these side by side, it might be a bit easier actually. If I put these side by side, cool. All right, so we have our constrained addition is in excess of our constrained production. So inflow exceeds outflow. So we expect our reserve to grow. So that's this black line, our reserve is growing. Our reserve is growing up until we've added all of our resource. So this drops to 0, right? And in this case, at this point, production now exceeds addition. Production exceeding addition, so our reserve is being depleted down until it hits 0. And once our reserve is depleted, that corresponds with where our cumulative production hits 1,000, right? And our reserve is depleted at 65 years. So on the flow side, we see at 65 years, it's depleted. Yeah, it's depleted around 65. Now, if I wanted to try some other things, for example, let's say we wanted our maximum reserve to be bounded. Let's say we can only fit 100 in there instead of infinity. So rather than overwriting it, I'm just going to comment it out. And then if I double click here, copy, paste, 100. So save that change. So now I'm saying, okay, instead of the reserve being unbounded, let's say the reserve can only take 100 megatons. So if I rerun that example now, how does that look different? All right, now we have this. Right, now we have this. So we'll put our stocks on the right. We'll put our flows on the left. So now our reserve is bounded. It can only accept up to 100 megaton. All right. So if we look at what's going on here, what do we notice? We notice that our addition is following the unconstrained curve. So this dashed line, again, that's the time series we pass in. This is what we would like it to do, but what it actually does is constrained. So this solid line continues to about, in this case, to about, I don't know, like a year and a bit. And then it drops off to match production. And it's matching production because our reserve is now full. So if our reserve is full, we can only continue to add resource at the same rate that we're withdrawing it. So that's why these two guys line up here. Right? And then on this plot, you'll notice that the slopes are the same. Right? So the rate of change of stock is the same for these two guys. Right? Because we're throttled by the finite capacity of the reserve in this case. If we go back to our home view here, right? So we're continuing until addition reaches 1,000, which is our total, at about 62 years. So over here at about 62 years, now this drops off to 0. We can't add any more. But at a certain point, we see our reserve starting to deplete. So our reserve is just starting to deplete around, say, 60. So if I go to 60 here, we see this is the point where our constrained production is crossing our unconstrained addition line. So now from this point on, production is exceeding addition. So we would expect our reserve to start deplete, and that's what we're seeing here. Our reserve will deplete to 0. It depletes to 0 by about 65. That lines up with where our addition, that lines up with where our production drops off. So once our reserve is depleted, so reserve depletion is happening before all of the resources have been added. So reserve depletion is coincident with loss of production in this case. For example, right? And then you can go through and you can just you can change stuff, save it, rerun it, see what kind of plots you get. And in this plotting method here, we have show flag is true and save flag is true. So if we go into where our script is being run from, we see our flows and stocks PNG files are being generated there. So I'm just going to go ahead and delete those. Because if I get rid of this breakpoint, I actually have a piece that helps clean stuff up at the end. So I'll just return this to its intended form and rerun it just to show how it works. All right, so there's the first example. Here's our stocks. Here's our flows. So if I close these guys down, the script will continue running until the next part. All right, so here's the second part. So here's our stocks. Here's our flows in this case. All right, and then once it's done, it just will clean up. It'll clean up the figures, so it'll get rid of all the figures that get generated as part of this. You can also change show flag to false if you don't want to see the pictures. You can change save flag to false if you don't want to see, or if you don't want to save the figures. And making sense of these input-output, this interface, that's what the documentation is for. So let's take a look at stocks and flows. Okay, so this is the constructor. So we see, put the documentation beside. So compare this to what's documented here. So we see the first thing that has to go in is our time array. So that's our time array here. The next thing that goes in is our unconstrained addition array, then our source array and our production array. And then after that, we have a bunch of default inputs. And what these parameters are is also documented here. So the time array years, right? This is what it means. That's what the time array is. This is what the unconstrained addition array is. For the default inputs, it shows that it defaults to 1,000. So if I don't pass anything in, like if I just delete this line, it'll still work. It'll just assume you mean a total resource of 1,000. The same for initial units. It assumes that the reserve is initially empty, right? But if I change this to something else, then I can have a different initial condition. Or if I just delete this line altogether, it'll just default to 0. Maximum reserve units, it's saying default is -1. If you put -1 in, it just assumes that it has unlimited capacity. So changing this to -1 is the same as it being infinity. I just left it as infinity because it's a bit more readable. I mean for the maximum reserve to be infinite. And then the unit string, this is just for plotting. So this defines what units we work in. Maybe if we want to be working in terms of kilograms instead of megatons, so I would just change that to kilograms. But in this case, it's megatons. And then similarly, if we go down to the plot method, so plot, right, you see the different inputs, and what they are is described here, right? So show flag is true, false. That indicates whether you want the plots to be shown. Save flag, same idea. Save path. This is where on your where in your file system you want the generated figures to be saved. So this is how you can use the documentation to make sense of what these inputs are and what it's expecting and how to use it properly. Okay, so that is looking at these, that's running these stocks and flows example using just the command prompt. But I did promise showing how to use it in Jupyter, so I'll do that now. So if we look at examples, there's this IPython notebook example that's provided. It's a Jupyter example. So for Jupyter, I'm going to use Google Colab. So if we go to Google Colab, awesome, Google Colab. All right, I'm already signed in. I'm just going to make a new notebook. I'm going to make a new notebook. All right, cool. And I'll just give it, I don't know, mech447 example. Just give it an arbitrary example. All right, awesome. So now we want to, actually I didn't need to do that. I just want to upload the notebook. Just upload a notebook. So I'm going to browse. I'm going to go to where I'm installed, examples, Jupyter example. We can upload that notebook. Yes, I want to leave the page. Cool. So here is the provided Jupyter notebook example. And this is, yeah, so I'm just selecting a couple of guys to install to show that it's working. And then it's running the same stocks and flows example that I showed previously, right? You see the plots being generated here, right? But to get this to work, the only awkward thing is we have to have access to the mech447 package. The instructions on how to do that are detailed here, but I'll just show you in this video. So there's sample data, but we need to upload. We need to upload this. We need to create a folder, actually. We need to create a folder. I should follow my own directions. Create a folder in this notebook session files. Okay, called mech447. All right, so new folder. Mech447. Okay, and then into here, we want to upload the contents. All right, so we need to upload, and then we need to everything in here. Yeah, I'll just I'll grab all of this, all the Python files. Just grab all the Python files and upload them into there. All right, so upload the contents of the downloaded into the folder. Blah 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 blah. Okay, so we've created the mech447 folder, and everything that's in our mech447 folder, all the Python files, all the .py, you need to stick them in here. Put them in there. Once you've done that, we should be able to run this. So if I just restart session and run all, I should be able to do, yes. Okay, so it's going to restart and it's going to run everything. Hopefully this works. Yep, there we go. All right, so that worked. So it's importing successfully. Everything's running. Yep, there we go. We're getting the same plots. Okay. So mech447, you can use it in a Jupyter notebook. That's fine. The only bit is you have to make sure that the package is available in your session files here. So we need to have a mech447 folder that contains all of these Python files. Right, that's what allows you to do these imports. But once you get past that, it's the exact same code as we saw in the command prompt example for running the stocks and flows model.